In this lecture also we will continue our discussion on sintering of ceramics. Earlier we were discussing about the three different stages of sintering: the initial stage of sintering, the intermediate stage of sintering and the final stage of sintering. We have described what actually mean by them and what kind of changes we expect in these three sequential stages. Here is a pictorial representation of the same stages. To start with, this is the initial stage where the particles are just touching each other and the contact is minimum and there is no deformation of the particle. They are the original particles which are put together. So, this is we start with, and then the second one, the B, it is the end of from this to this, actually the initial stage. Okay. We can say it is initial, not the initial state, it is the starting point. These are this is the starting point, and then the changeover which takes place from this to that, whatever the time frame is and whatever the physical changes or geometrical changes takes place, that includes the initial stage of sintering. Here you can see some neck growth, it is called the neck growth. That means the two particles which were in point contact, now the contact area has increased from this to this. This is actually a circular contact, in the 2 dimension we are seeing only the line, and in addition between these are 3 particles. So, you have a contact area somewhere there and another contact area there. So, this third particle is touching this particle and that other particle somewhere here in the form of another neck area. So, there are 3 different neck areas between one between these 2 particles, another between these 2 particles, another between these 2 particles here. So, when, as you have mentioned earlier, when about 20% of neck growth has taken place, then we say the initial phase is over. Then we go to the intermediate stage, when, as you can see, from this to this there is quite a significant change in the geometry of the particles which were spherical in shape. Now, there is a polyhedron, large number of polyhedron are put together because more and more contact area has increased, a planar surfaces has created between the 2 particles, and therefore, we have more of polyhedrons, different kind of polyhedrons has been formed. Some of these polyhedrons are actually these polyhedrons are basically grains now, having different faces, planar faces. One can say ideally one can have a dodecahedral kind of configuration, but such kind of ideal situation really do not take place. We do get different forms of polyhedra, and pores which was in between these particles, interstitial spaces between these particles are now getting distributed along these grain boundaries, mostly along the grain boundaries. These are the pore phases. So, this is a continuous channel of pores. Once again it is quite idealized, it is not exactly what we get in reality, but something like this happens. Okay. So, the pores are still continuous, the solids are still continuous. So, that is the kind of up to the end of the second or the intermediate phase, both pores and the solid phases are continuous, right. Of course, the solid phases, total volume of the solid phases are much larger, because 90% of is occupied, 90% of the total volume is occupied by the solid, only 10% is actually the pores, and these pores are, when you want to have a continuous phase, naturally the dimensions will be more linear in shape or a cylindrical kind of dimensions. So, that is what you get here. and the final stage pores are at the corners of the polyhedra. Unfortunately, these pores are not properly drawn here. Actually, these pores are not properly seen. It has been the only difference between here you can see these boundaries are much thicker here. These boundaries are much thicker. Actually, this thickness is basically because of the pores, okay, whereas these boundaries are much thinner. So, those pores have been shrunk. The boundaries has thickness of the boundary has become less. There is no pores in between. So, the boundaries has become shrunk and they more or less a line contact now, whereas the pores are not, unfortunately is not shown here properly in the drawing. The pores either will be at the corners, this triple point boundaries like this or like this here. So, most of them pores will be at the triple point boundaries, or some of the pores may also be within the grains, that what we discussed earlier. The pores are now discontinuous, okay. No longer the pores are continuous like this. What happens in the throughout the second stage or the intermediate stage, to the final stage the pores becomes discontinuous phase, and only about less than 10% is remaining, and therefore, it cannot be continuous anymore. So, but the sites where these pores will be there is primarily at the triple point boundaries, either here or there, okay, or somewhere here. Most of them will be like that, but few of them may be under certain situations may be within the grains itself. It is again not shown here, but we can imagine some pores might be here, or some pore might be very small pores might be there, that is what we call the residual pores. Okay. So, as a result of mass transport and the change in the geometry, the pores are not only becoming smaller and smaller, the volume becoming smaller, the sizes are also become smaller, and from a continuous phase up to this intermediate stage they will be discontinuous at a later stage. And sometimes you will find later we will discuss that once they become discontinuous, the pore removal becomes much tougher and tougher. Okay. Sometimes it becomes almost impossible to remove the last traces of the pores, and so getting a theoretical density becomes almost impossible. But more than 99% or even between 95 to 99% pore removal is possible. It does not take a lot of difficulties or difficult steps. Okay. So, this is the kind of pictorial view of the progress of sintering, what happens in the total phenomena, and how they can be subdivided into three different stages. Having discussed all these things, now we go to little more details. The atomistic or atomic mechanisms of mass transport during solid state sintering. We have earlier seen that there are basically two types of sintering. One is a solid state sintering, where there is no presence of liquid, and another is the liquid phase sintering, where there is a major quantity of liquid is produced to enhance or to facilitate the sintering process. Here we are talking about the solid state sintering. Now, in the solid state sintering, of course, the mass transport has to be there, and we have seen there are two major mechanisms by which the mass transport can happen. One is the evaporation condensation, that is when the vapor pressure of the solid is quite high. If the vapor pressure of the solid is quite high or it is very close to its melting point, the vapor pressure of course increases quite substantially, and in such cases evaporation condensation mechanism is predominant or is the dominant mechanism, whereas in most of the cases, most of the oxides, have a diffusion mechanism, diffusion by vacancy mechanism. Mass transport takes place not by evaporation condensation, but by diffusion, and that again the diffusion can take place by many different mechanisms. Out of that, vacancy mechanisms is normally the predominant mechanism by which sintering takes place. Third one of course is a viscous flow. This is not in presence of a liquid, but the solid itself becomes little bit viscous in nature, and particularly at the grain boundaries, and that also facilitates the mass transport along the grain boundaries. So, that is also another mechanism. We will discuss briefly about that. Our main discussion will be on these two, what exactly happens in the atomistic scale by these mechanisms. To start with, we will first take up the evaporation condensation mechanism, what exactly takes place at the atomic level, how the mass getting transported, and what is the phenomena which takes place in such situations. Now, what is the driving force evaporation condensation? We have already seen that there is a difference between vapor pressure, difference of vapor pressure between the convex and the concave surfaces. So, just because the change of curvature sets up a driving force. Now, here what it happens, if we are just taking up a two spherical particles, of course, in this case they are uniform in size, same size of spherical particles. That is how when they are compressed or they come together, the conglomeration of particles. So, this is the contact area, or the contact in theoretically it is actually a point contact, but otherwise in reality there may be a slight finite volume or finite area. Now, once this contact is made, there are two types of surfaces created. This is the convex surface. Okay. This is a spherical surface, spherical convex surface, but at the point contact, a very small concave surface is also formed. Okay. So, once a small contact area is developed, you have mostly it is a convex surface like this, but at this point of contact you have a concave surface also. Okay. This is the concave surface, and because of that there will be a difference in vapor pressure. So, more amount of vapor will be generated on the convex surface, the vapor pressure on the convex surface is more. Therefore, more and more amount of material will get evaporated from these surfaces. All these convex surfaces, free surfaces, of course, there should not be any other contact, there may be other particle coming in contact, then there will be another concave surface and so on. So, wherever there is a contact, there will be a concave surface, and that concave surface and this convex surface makes all the difference. So, the vapor pressure will be much lower here because of the convex character, whereas for the convex surface the vapor pressure will be high. So, there will be vapor pressure gradient, and obviously from the higher pressure material will try to flow to the lower pressure to dequalize them. So, the material transport will go through the gas phase, it will not through the solid phase, but it will evaporate here at different points of course, and then there will be some vapors of the same material in the gas phase, and because there is a concentration gradient, much lower pressure vapor pressure is there. So, they will try to condense that. Okay. So, the vapors will evaporate, or the material will evaporate here and try to go to the vapor phase, the gas phase and finally condense at these concave surfaces, okay, surrounding in the form of a circle actually. Okay. So, from all these surfaces material will come and deposit here. Okay. So, it is not because of the temperature gradient, it is not normally if you heat to high temperature and then there is a cold zone, the material will normally deposit at the cold zone, but this is not because of the temperature gradient, it is because of the curvature change. Okay. Even at both the points at the same temperature, this material will be transported from here to there, and that is the very simple mechanism of evaporation and condensation mechanism. So, from the convex surface the materials will get evaporated, and at the concave area the material will condense, and because of its condensation the concave area will slowly grow, and that is what happens. More and more material has deposited and this area has increased. This area from a point theoretically point contact area has gone to a circular area, okay. And this radius of curvature now has changed, now is changing also, which was more convex now becomes more flatter. Okay. So, these will be more flatter. So, more material will be evaporated and come here, and this will grow, the contact area will grow automatically, and this will be flatter and flatter till the pore shape is also getting changed. As you can see, the corners are getting reduced, it is more becoming I mean less concave, more and more the radius of curvature is also going to change. So, in this process the center of this particle to or the distance between the two centers is not going to change. Okay. This particle will not come closer to each other. This total distance, in fact, one should have drawn from the center to center and this center to this center. So, it is about if the same size is there, it is about the diameter of the distance is about the diameter of the each sphere. So, there is no change in dimension. Okay. The overall dimension is not going to change by this kind of a mechanism. If this is the mechanism by which the sintering is taking place, the result is there will be no change in dimension, there will be no shrinkage, no densification. That is also another very important, although by definition sintering do give rise to densification, and that is one of the major effect of sintering, but in this particular mechanism evaporation condensation there is no densification. What does it mean? There is no densification, but even then there is a sintering. Now, densification is not a necessary condition for sintering. More important condition is the mechanical strength, this whether the particles, the agglomerated particles or consolidated particles do have a better strength after sintering or not, that is a more essential condition. Okay. So, in that context there is a bond area, increase of bond area, because there is a point contact originally. Now, we have a much larger contact, larger area of contact here, and therefore, there is an increase in the bond area. So, there will be enhancement of strength. So, this is more essential parameter or essential property after sintering or as a result of sintering. This may or may not happen, okay. Particularly in this case it is not happening. That does not mean that it is not getting sintered, it is getting sintered because the bond area or the contact area is increasing, and consequently there is a enhancement of mechanical strength. So, that is a important consideration. So, I think it is very clear now that material is getting transported from the convex area through the gas phase to the concave area, and that is how the concave area or the contact area is slowly increasing. So, this is what we know about the basic physical process which is taking place in evaporation and condensation mechanism. Well, with this physical concept, let us try to look at the rate equations, whether we can write some equations relating the different parameters, the time, the temperature, how the growth is taking place and what rate it is taking place, what is the time dependence, temperature dependence, even is there any particle size dependence of this rate. This is for that we once again take the same example, same pictures. Here we have introduced few parameters. We have introduced r, the initial radius of the spherical particles. So, once again our assumption is we are having uniform size spherical particles, not of different sizes, all of same size, and they have a radius of r. Rho, we also define a radius of curvature rho at the neck area. So, this is a concave surface and the radius of curvature is rho, okay, that is what we define. Another term or another parameter we also like to define is the x. The x is the actually half radius of the contact area. Okay. Here it is half the length. Okay. Here in one dimension or two dimension or one dimension, in fact it is actually a two dimensional circular contact area between the two particles, and the radius of that circle is actually x. Okay. Radius of that circle is x. So, this distance from here to there is actually the diameter, this is the diameter of that circle, and so it is 2x. Okay. So, actually it is x is the radius of that contact area, the flat circular contact area. Now, if we define these parameters or take into consideration these parameters, then we can write an equation of this form. The pressure difference between the convex surface of the spherical particles and the neck region, the concave surface actually, neck region is given by this formula which can be derived, but this has not been derived here. We have just taken the delta P, the pressure difference. Once again this is related to the Vmx, that is the volume of the one volume formula unit mx, provided mx is the compound of which the particles are made of. Then P flat, P sub flat is actually the vapor pressure, or sometimes it is also called the partial pressure, vapor pressure of the flat surface, that is the reference material, reference surface, and then gamma SB is the solid to vapor surface energy, solid to vapor surface energy, Kt is the Boltzmann constant, temperature time, T is the temperature, and here there are two radius of curvatures actually. One is 1 over rho, another is 1 over r. R is the radius of the sphere of the initial particle size of the sphere, spherical particle size, and rho is the radius of curvature of the concave surface or the neck region that we have defined earlier. This is rho, this is x, and this is r. X has not come here so far, x will come later. This can be, since rho is much smaller than r, compared to the radius of the initial spherical particle, the rho, the neck region, the radius of curvature of the rho is much smaller, because it is a very sharp peak, sharp radius there is although concave, but it is a very sharp change in radius, change in curvature. So, the radius of curvature is much smaller than r. So, if that is so, this becomes 1 by rho only, okay, 1 over r can be neglected, and that becomes equal to this term multiplied by 1 over rho. That is what you get here. Then from the geometry, one can also correlate these two terms, or these two parameters, these three parameters in fact, both r, rho as well as x. Here again it is shown what is rho, what is x, and r is not shown here, r was shown in the earlier picture. So, one can write r plus rho square whole square equal to x plus rho whole square plus r square. So, that is another, it is pure simply from geometry one can write that. And once again, if x is equal to, x is also less than r, that means earlier you have seen rho is very less than the r, this value. We are also assuming that the x is much smaller than r, then the equation may be approximated as rho equal to x square 2 by r minus x, which is approximately equal to x square by 2 r, x square by 2 r. Once again x is neglected, so it becomes 2 r and x square remains there. So, rho becomes x square by 2 r. Now, that was the geometric relationship, and then we have earlier seen the delta p, which is the driving force. Delta p we have equated, we have got some equation relating delta p and the radius of curvature, and then we have also seen how the radius of curvature is related to the other geometric parameters x and r. This is another both rho, x and r, these all the three geometric parameters are also related. And then we find what is the rate of neck growth, at what rate the material is getting deposited. The driving force is delta p. Okay, so, the delta p is the term which basically determines at what rate the material is getting deposited. So, the dx dt here, that means the rate of growth, more the material more the material gets transferred from here to here, the x grows. Okay. So, that is also a measure of the rate of change of x, or the rate of growth of x is actually a measure of the sintering rate. Okay. So, that is also basically the sintering rate, that is how we have defined the sintering rate here. So, this is the sintering rate, or the rate of change of x as a function of time, and that will be equal to J. J is the basically the flux is the flux of the evaporated vapor, and is given by the Langmuir equation, which we will discuss later. But before that, it is the flux into the atomic volume of the compound, or the molecular volume of the compound. So, and J is the amount of the material flowing in per unit cross section. So, that is the flux. So, and that flux again depend on the delta p, what is the pressure difference. So, the pressure difference and the flux is of course proportional, but with some other terms if you want the exact numerical or quantitative equation, quantitative equality. So, that actually J can be, this is called the Langmuir equation, which is relates the flux and the vapor pressure difference between the two sides. So, this becomes alpha and root over 2 pi m x k t. Here again there are some terms have been introduced, where m x is the I think there is a mistake here, subscript m x is the molecular mass, it is mass now, not the volume, molecular mass of evaporating solid, and alpha is an evaporation coefficient. Once again the alpha has been wrongly placed, sorry, I need to change that. So, to continue with that rate equation, combining all the relevant equations and integrating the final expression for the rate of neck growth, that is how normally this x by r, this x by r ratio is actually termed as the neck growth, or the x as a relative to the particle size, initial particle size. So, that is a kind of kinetics or the growth of the sintering process. That means how the x is increasing, x is increasing from 0 to some value and with respect to r. So, this becomes this kind of an equation. We are not going to the details, this is the final equation, but it gives us a lot of clue how this reaction is changing and what are the different parameters which controls this behavior, or which controls this phenomena. 6 alpha gamma is V, V m x square, and P flat, P sub flat means the vapor pressure on the flat surface, and then in the denominator you have root over 2 pi m x, that is the mass of the formula unit, and K and T temperature. This is to the power 1/3, and then there are two other terms, two other parameters, which is time, T is the time, and then R is the initial radius, okay, initial radius of the particle, and that is raised to the power minus 2/3. Okay. So, this is a quite a complex relationship, but it gives us very important informations so far as the dependence of this process on different experimental parameters are concerned. So, this equation predicts the rate of neck growth, okay, how at what rate with respect to time, how it is growing and how it will grow. Obviously, there are different material parameter as well as experimental parameters which determines this rate. Now, the neck growth is initially very high and then slows down, because with time the exponential the exponent is about is 1/3. Okay, it is certainly not linear, it is a curved relationship, and initially with lower values of t it grows quite fast, but as we increase the time it slows down, it becomes more or less constant after some time, and almost at it as it reaches the 100% density or 100% growth, the rate becomes very slow or almost nil. That is one information we get from this equation. Then the number 2 information is it decreases with increasing particle size, because r is here, r is the initial particle size. Now, this is inverse, this is or this is negative. Therefore, larger r means the rate is slow. Okay. Higher is the r, the rate will be slow, x by r will be less. So, it decreases with increasing particle size. So, higher is the particle size, the sintering process will be slower and slower, and that is the reason when you are talking about to getting a very 100% dense material, you have to have very fine particle size to start with. Okay. A millimeter size material may not sinter at all, whereas a micron size or a nanometer size particle will sinter much faster. So, that is the reason particle size is very important. Particle size is very important in the sintering process. So, it is not only the temperature, temperature effect of course will come later, just now in a minute. It is time, of course, is the anyway the rate determining factor. Larger the time, the densification will be more. Of course, in this particular case there is no densification, but the sintering will take place, the neck growth will take place. Okay. So, even if there is a neck growth, there is no densification, that we have seen earlier. So, both time and the initial particle size are the two most important parameters which actually determines the sintering process. But another very important parameter is the temperature. Okay. Now, temperature has a little tricky effect here. For example, temperature here is in the denominator. So, as if increasing the temperature will decrease the rate, okay. But it is not so. It is not so. The temperature here is, the temperature is there, but more important temperature effect is here. Okay. This will not change too much with temperature. There will be slight change in gamma, of course, but not much. But the more important effect is here in the vapor pressure. Now, the vapor pressure, it has not been shown that the vapor pressure is an exponential, exponentially depends on the temperature. So, higher is the temperature, vapor pressure increases exponentially, whereas this is a denominator is in the root, okay, only to the power half. So, the temperature actually comes in the form of the vapor pressure. So, increases with increasing vapor pressure of the solid, that is quite obvious. Vapor pressure means this one is increasing as it increases directly, almost it is not directly proportional, the 1/3 exponent is there. So, but it is proportional to this, directly proportional, actually it is not linearly proportional, and the temperature effect is dominated by the exponential dependence of the vapor pressure, not by this denominator term, it is dominated by this term. So, the vapor pressure increases exponentially with temperature, and therefore, the x by r also will increase quite significantly with temperature. So, there are three different parameters which actually determines the rate. One is of course the time, then the initial particle size and temperature. These are the three things which one has to take care to control the sintering process for evaporation and condensation mechanism. Of course, this has been derived for evaporation and condensation mechanism although, but very similar things are also valid or very similar situations are also valid for the other mechanisms, as we will see in few minutes. Well, so that was all about the evaporation and condensation mechanism. Once again, I will just try to recapitulate that going back to the particular picture or the figure here. One of the things we have concluded that there is no shrinkage. There is no shrinkage because the material is not getting removed from here. Okay. If the shrinkage has to take place, these two particles has to come closer. okay. But it is not happening. On the other hand, some extra material is getting deposited. That is how the neck growth is taking place. Okay. So, there is no dimensional change, overall dimensional change is not there, only the shape of the pores are changing. Okay. Shape of the pores are changing, which was a very sharp corners here in the pore, because this part is the pore. Okay. This part is the pore. So, which is a sharp corner, it has been a slightly less sharp corner. So, the shape of the particles will shape of the pores are changing, but there is no change in the overall pore fraction or percentage of the pores. So, that is a very important thing one must remember, where this is in comparison to the next mechanism, which is the vacancy mechanism. This is the vacancy mechanism of solid state sintering, and there, as you have seen, the concentration difference is in opposite direction. That means, at the concave surface here, once again there is a neck growth here, same thing. At this point there is a concave surface, and away from that point is there is a convex surface. So, this convex surface, the vacancy concentration is low, whereas at the concave surface the vacancy concentration is high. So, the vacancies will move from this concave surface to the convex surface. So, the movement will be opposite so far as the vacancies are concerned, compared to what we saw in case of vapor deposition or vapor transport. So, from this region the vacancies has to move out. Now, vacancies moving out means there is a void is created, and that void will be filled up by the materials or the atoms from the surroundings. Okay. So, if a vacancy concentration, the vacancies are moving out, there is a high vacancy concentration, the vacancies are moving out, which means the material is getting filled up here. Okay. So, that is the situation. So, that is what is happening here, the vacancies are going out and the material is getting deposited from this to that, or the from this to this end. So, ultimately it forms a neck in the form of a grain boundary, what we call a grain boundary region. This is one crystal, this is another crystal, and the boundary is basically a grain boundary. So, from the grain boundary region the vacancies are moving out towards the convex surfaces. Okay. Now, this movement can take place again by three different paths. The movement of the vacancies can take place in three different ways, or three different paths can be followed by this movement. Now, for this movement, one is, these are the three different paths which has been designated here or shown here also. The vacancies are moving on this through the lattice, through the solid, through the bulk of the solid. Okay. So, this is called volume diffusion or lattice diffusion. That means, the vacancies, that is the point defects which are being created here or generated here because of the high concave surface or very strong concave surface, or one can say a very small radius of curvature of the concave surface is a negative curvature, and so large concentration of vacancies are already generated because of this curvature, and that has to go out to equilibrate. So, if the sufficient thermal energy or the activation energy is provided, this high concentration of vacancies will tend to redistribute itself, and it will go towards the convex surfaces. So, it can come here, it can go there, it can go there and so on. So, everywhere it will get distributed, and this distribution can take place either by this path through the bulk of the volume, a bulk of the solid, which is called the volume diffusion or the lattice diffusion. It can go through the surface, okay. It can just very near to the surface, it will not go to the bulk of the solid, but the vacancies will move along more or less along the surface, just near the surface, and that is called the surface diffusion. Or this can go like this, the vacancies which are generated here or the vacancies which are generated there will go inside, okay, go inside, because this becomes a flat surface, this becomes a concave surface, a convex surface. So, there is a gradient between this point and that point. The same thing, there is a gradient between this to that also, okay. Although the gradient is less, but the compared to the flat surface, this is also more. So, the vacancies can go along the grain boundaries, okay. So, basically at this point the vacancy is the highest, vacancy concentration is highest here, and the vacancy concentration is less here and also relatively less there. So, the vacancies can move from this to this towards that, or from this towards that, and then here from this along the surface or along the bulk. So, there are 3 different paths which the vacancy can follow, and accordingly there are 3 different mechanisms, and the rates are also will be slightly different. So, the direction of the arrow indicates the direction of the vacancy migration, okay. Of course, here it is slightly misleading maybe, actually it is vacancy is moving from this point to that point or from this point to that point, okay. That possibly has not been drawn well. So, but the vacancies are moving along this line, which is basically a flat surface. So, the mass transport is in the opposite direction. So, when vacancies are moving out, materials are moving in, or in fact because of the vacancies the materials are slowly coming in, and there will be a collapse, of this surface, okay, or they will come closer. So, as a result of this vacancy mechanism, unlike evaporation condensation, we have a change in dimension. This d, this distance will be less, d minus delta d. Okay. So, after the growth of the neck, there will be a change in dimension. So, that is one of the most important effect of vacancy mechanism as compared to evaporation condensation. Now, there are 3 different mechanisms or different paths the vacancy can follow, and that is why the 3 different names have been given as mentioned earlier also, the lattice diffusion, the grain boundary diffusion and the surface diffusion. And the equations for the rate equations are also different. We are not going to the details of that, but more or less in the same manner which we have done in case of evaporation condensation, one can go through that kind of analysis, mathematical analysis, and find out this kind of a rate equations. Yeah. Once again, the ultimate parameter which we would like to determine is the x by r in each case, as also in the case of evaporation condensation. Only thing, we have introduced few more terms like diffusion, d is the diffusion coefficient here, instead of vapor pressure, earlier we have used vapor pressure, here it is diffusion coefficient all through it is diffusion coefficient of one type or the other. This is one kind of diffusion coefficient, this is another kind of diffusion coefficient, this is another kind of diffusion coefficient, but they are all diffusion coefficient of the vacancy movement, and these are D subscript MB. We will define that. What is that actually? It is ambivalent, D ambivalent or the ambivalent diffusion coefficient, and then GB is the grain boundary diffusion coefficient of the same vacancy, and then the surface diffusion coefficients. We have introduced three different paths, all of them are diffusion coefficient controlled by the diffusion coefficient, but the values of the diffusion coefficient, their activation energies will be different. That is why different terms have been used here. Okay. Then of course, these numerical values are of course again different, one is 64, another 192, another 125, but everywhere you have the gamma, the surface energy, surface to solid vapor surface energy term, everywhere it is there. This term is also there, okay. M square x mx square is also Vmx square, but here it is only Vmx, it is linear, not the square. Okay. And then you have another two terms here, which is delta Gb and delta S. That term is not there, the first one, that is not there, and Kt of course denominator Kt is all the time present. So, delta Gb is actually thickness of the grain boundary, and delta S is the thickness of the surface through which the vacancies are moving, that is the path which is following. Okay. And then these exponents are different, in one case 1/4, 1/6 and 1/5. Okay. So, it is not too difficult to remember, but once again they are not that significant, but the exponents are certainly there. Then these two terms are as usual there, the time term and the radius of the initial spheres or the spherical particles. Spherical particles are there, and then these exponents are also different. One is 3/4, another is 2/3, another is 4/5. So, obviously their dependence on the particle size are slightly different, but they have all negative exponent, which means higher is the radius of the higher is the particle size, lower will be the rate, lower will be the net growth. Here again, as time increases, the net growth increases obviously, but at different rates, the slopes will be different, and one will be reaching the plateau faster than the other. In all of these, it is the slowest species along its fastest path that is the rate limiting. Well, there are different, we are talking about the vacancy mechanism, but we have not talked about which particular vacancy. Is it the metal vacancy, it is the oxygen vacancy. If it is a more complex oxide, there may be 2 or 3 different cations, there may be 1 cation or 2 cations. So, all of them have different rates of diffusion, all of them may follow the vacancy mechanism for diffusion, but their rates will be different, which we have not talked about here in this particular case. In fact, the so called ambivalent diffusion coefficient takes care to some extent of that particular situation. This is which we have already told you that these are the different parameters, but this is ambivalent diffusion coefficient for the compound itself. Okay. because it is the compound which is diffusing or moving. So, but when you talk about diffusion coefficient, the compound as such is not moving, is moving by either through a vacancy of this or a vacancy of that, one of them will be predominant. So, the diffusion coefficient of the compound is something like this. This is the diffusion coefficient of the metal, diffusion coefficient of the anion or the cation and the anion, and then diffusion coefficient of the cation and anion. So, this D subscript Mb, that is the ambivalent, ambipolar, not the valent, sorry, ambipolar diffusion coefficient. I beg your pardon, this is ambipolar. I might be telling ambivalent, it is not ambivalent, it is ambipolar. Ambipolar diffusion coefficient for the two different ions or the cations, one is the cation and the anion is related like this. Okay. So, I think the time is up. So, we have to complete this discussion here or close this discussion here for the time being, but we have some more thing to discuss so far as the sintering is concerned, and we will do that in the next class. Thank you for your attention.